Okay, good afternoon. For some people in Japan and also some people in Taiwan, today is my great pleasure to have Dr. Ting-Yang from CISA in Italy, and he's going to share with us his recent result on synchronization in Kuramoto models. But today he is going to tell us how to define there are several notions of synchronization, and maybe he will also talk about how to prove the number of equilibrium is finite. And I am very curious about this result, so let's welcome him.
Hi, hello everyone. Thank you for the introduction from Dr. Dai, and it's my honor to be here to give a talk. First, I would like to thank you, Jiayuan, for inviting me here to give a talk. And can everyone see my screen for the slides?
Yes, it's very clear. Yeah.
Oh, okay. So, okay, let me do something like this. Okay. So, let me introduce myself very short. So I was graduate from National Taiwan University, and when I do my master, my advisor was Professor Junquan Chen, and during that moment, I was doing biomath, and we still do biomath together recently. And today's topic is for the synchronization, and we especially focus on the Kuramoto model. And of course, this is different from biomath, but I will try my best to explain everything clearly. And right now, I'm doing postdoc in Italy, CISA, and this is the joint work with my friend Yunfeng Luo, and he is my previous advanced calculus TA, so I'm happy to work with him. And the other co-author is Winnie Wen, and she's my girlfriend. And finally, and Winnie Wen, she's working in the National Taiwan University right now. And finally, Chen Bingzhu, he's my PhD classmate, and we are also a very good friend with each other. Okay, so today's topic is synchronization as an equilibrium phenomena in Kuramoto flows. Okay, so I will explain more later. Now, in section 1, I want to give a short introduction for the application for the Kuramoto. I know a lot of people are expert in this model, and I try to explain this for everyone. So forget about me. And so the Kuramoto model is a fundamental paradigm for synchronization phenomena and has wider range application across different scientific fields. So for example, in physics and engineering, it raises a problem such as power grid and the Josephson junction arrays. And in complex systems, it describes the collection behavior, including the neuron synchronization and biological rhythms. And also, I think the Kuramoto model serves as a conceptual bridge between the statistical physics and applied mathematics, linking the final dimension dynamics and the mean field descriptions. Okay, so I think Kuramoto is very interesting and deep in both science and math. Okay, and of course, very short history. Kuramoto in 1975, introduced Kuramoto model, and so he tried to use this model to describe complex system, and this picture is in 2023, okay, and this is Kuramoto, and I borrow this picture from this magazine. Okay. Now, this is the model that we want to discuss today. So for the first half of the talk, I will talk about the real Kuramoto model, and I will try to unify different concept of synchronization. Okay, so in the first half talk, we want to consider this Kuramoto, second order Kuramoto model with the inertia, with the damping, and the different nature frequency, and finally with very general coupling coefficients. Okay, and so for the inertia, we consider m is larger than 0, d is larger than 0. This is nature frequency belonging to nature number. And lambda is the coupling constant. And in this talk, of course, we consider a group of oscillators. So the connection is described by undirected graph G, and the G is kinetic. Okay. And also we consider the symmetry for the coupling coefficients. This means this. And of course, we don't have, so if k is equal to j, then this term is 0. But for convenient, we set lambda jj is 0. So this means that we don't have self loops. Okay.
Sorry,
and
sorry, can I ask a question?
Yes.
So your lambda
Yes,
can,
yes,
be,
sure.
can be negative.
Yes,
Your
yes.
lambda jk can be negative. Okay.
Yes, 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 yes.
So this is not a standard Kuramoto, right?
Yes, yes. So it's like a mix with the absorption and the repulsion types.
Yeah.
Yes, yes, you are right.
Thank you.
Yeah.
Okay.
Yeah. Yeah, thank you for the question. And everyone can interrupt me at any time. I will try my best to explain more clearly. And the other things that we want to double check is this one. The variable theta is in R. And a lot of people will set theta in torus, but although they are equivalent, but I will explain more later. But right now, we set theta inside R is because we want to use energy argument later. So this means that the phase lock state will imply the frequency synchronization. Okay, I will explain more later. Now, in these slides, I will, because our goal is the synchronization as an equilibrium phenomena, right? So why we can do this is because we choose the rotating frame. Okay, what does this mean? This means that without usual generality, we can assume the sum of nature frequency is 0. Okay, what does this mean? This means that here, the sum over omega is 0. Okay, so if we sum over this equation with the subnotation j, then this term will disappear, right? Also, because of the symmetry property, all of the signs will cancel by each other. So in some sense, we have some conserved quantity just based on these two, right? Okay, this will be helpful later. So why we can choose this? This is because we just choose this change of variable. Okay, here, of course, the theta dou become here, and double dou is this. And as everyone can see clearly, the sum over this quantity with the notation j is 0, right? Because sum over this and sum of this are equal to this one, right? The denominator term here, right? So in this co-rotating frame, we have this assumption, okay? And this is, we don't change anything, okay? We just choose this frame, okay? Next, we are ready to define the definitions of synchronization state. Okay, so we have several different definition of synchronization. I mean, in in Kuramoto community, and I collect most of them. The first one is called full phase lock state. Okay, what does this mean? This means that there exists a constant, and the theta j minus theta k tends to this constant for all jk. So we have a lot of different constant, but all of the difference will tends to the constant. Okay, so this definition is quite clear because in some sense this represents the synchronization state will tends to a equilibrium point, right? Okay, the second one is called phase lock state. Okay, a solution phi theta is called phase lock state if there exists a positive constant L such that the difference between theta is bounded by L for all jk. Okay, so this means that we have the length of L and all of the theta will inside the L. Okay, so of course, based on the definition, the first one is stronger than the second one, right? So if you are a full phase lock state, of course, this will imply that state is also a phase lock state, right? Because the first one will tend to. Yes,
okay.
Yes.
In your
Yes.
phase lock state, is L modulo 2 pi or arbitrary positive number?
No, not 2 pi, not 2 pi. So in R.
In R.
In R, yes.
So if we observe an oscillator on a circle, then we cannot distinguish different L, right? If L is a modulo 2 pi, I mean, this phenomena cannot be observed on the circle, right?
Yes. So on the circle, yes.
Thank you. Yes. But then L can be 2 pi, 4 pi, 6 pi, 8 pi.
Yes, that's true. So in a circle, if we have some phenomena like called driving, this means this will rotate the circle permanently, right?
Yes.
And if you lift this torus onto the R, this means you will have a solution which is unbounded.
Yes.
Right. So if we discuss theta on Rn, this gives us an advantage. What kind of advantage? If you have a phase lock state, then this is really a bounded solution, right? Because on the torus, the solution is always bounded, right?
Yeah.
Okay. So, but later I will thank you for Jayan's question, because later I also want to discuss the thing on the torus because I want to apply the Poincare-Bendixson theory. Okay, so the third thing is frequency synchronization state. Okay, so what does this mean? This means that the frequency tends to 0 for all j. Okay, so right now in the Kuramoto community, these three usually are used in for the mathematicians. Okay, because these three definition we can in some sense manipulate this definition, right? So it's more easier for us to prove something rigorous. Okay, and of course our goal is I want to show in generic coefficients, in generic topology structure, these three are equivalent to each other. Okay, so this is the first goal. And the fourth definition, I call this order parameter synchronization state. Okay, so before doing this, of course we want to define what's order parameter. Okay, and the list quantity was first introduced by Kuramoto himself. Okay, so the concept is we have a solution theta j, okay, and we times I and put them onto the exponential and sum over them. Okay, so the first thing that we need to know is the magnitude of Z is just R, right? Because R and capital theta is, I mean, this is a way to express a complex number, right? And so the magnitude of Z is just R, and the maximum of the R is 1. Because if we take the absolute value here, which is 1, then we have n over n is 1, right? So a lot of people say, especially physicists, they say, oh, if R is close to 1, then we have a synchronization state. Okay. If R is small, then it's not. Okay. And in this paper, I mean, in this talk, I define what's the synchronization in order parameter sense. Okay, this means that there is a z star which is a fixed constant, such that the limit of z is z star. Also, z star will pass over a threshold, and the threshold is just depend on the nature frequency. Okay, so for the O2O topology, I will show that these 4 definitions are equivalent to each other. This means that the intuition from physicists is correct. So their intuition is if the Z will over a threshold, then this means synchronization, right? And this synchronization is consistent to the definition from mathematical communities. Okay, but I need to emphasize this is only for the O2O topology. Yes, please.
Why is lambda here? I don't understand. Lambda z
lambda.
Yes.
Sorry. Lambda is in our model. Lambda is here. So because we only consider O2O, so lambda is equal to lambda is a constant. Lambda jk is equal to lambda is a constant.
But when we say O2O, it's about the network topology, right? If you have a lambda jk, it's also O2O. What do you mean by? I mean, uniform couple. Uniform couple.
Yeah. Yes. I mean, different people use different. Sorry, I should explain this more. So for me, the O2O topology means lambda ij is equals to a constant, and this constant is just non-zero constant.
But usually for me, the O2O is you have this summation to everybody.
Yes. Okay, I see. That's more general, I think.
Okay. Yes. Okay. Thank you. Okay.
But for me, the weight should be the same. Okay. And that's important for us. I mean, if you consider more general case, I don't know how to do it. Sorry, but let me explain first, and maybe we will have different idea later.
Can you go to the next slide?
Yes.
I have a question. Next slide.
Yes.
Next.
Definitely.
Next one.
Okay. Next. This one.
Next. No.
This one?
The classification, the notion of synchronization. Yeah.
Yes.
So your Z is a complex order parameter, right? Right.
Yes.
Many people they describe synchronization by the real order parameter, which is your capital I.
Yes.
If I define if I define your OPSS for the real order parameter, is the equivalence true or not?
Oh, this is a good question.
Because
so based on my
I think your OPSS implies are converged, right? But not conversely.
Yes, you are right. So yes, thank you for pointing out this point. So so for us, the condition for OPSS is slightly stronger, I think. Yes. So that's a good point, and the answer is I don't know how to do it.
Okay.
Yes.
Thank you.
Yes. Yeah, no problem. Maybe we can discuss later, and maybe you will. We can try to do. So this is the picture for the resource that we have. So for generic topology, full phase lock state phase lock state and frequency synchronization state are equivalent to each other. Okay, and if we consider all-to-all topology, then these four concepts are equivalent to each other. Okay, so this is the picture that we can see. Okay. Next, because we want to handle the general coefficients. So general means general M, general D, general omega, general lambda JK. So we want to define what's our parameter space. Okay. So first, we define frequency vector omega, and omega only have n minus 1 components from omega 1 to omega n minus 1. This is because we already have a constraint, right? So the sum over omega is 0. This means the degree of freedom for omega is just r n minus 1, right? Also, we consider the no-self loops and consider symmetry for the lambda jk. So the degree of freedom for lambda is this number, right? Okay, so we consider omega in R n minus 1, and we consider coupling coefficient capital lambda in R n times n minus 1 n over 2. Okay, so our parameter space is just this times this. Okay, so this is our P. Okay, and I mean, I will remind everyone later again, so no problem. So let's define what's generic coefficient.
Sorry.
Yes, yes.
You
yes,
have an
please.
inertia, you have a second order, you also have a DJ, MJ, right?
Yes, yes, yes.
So
but that coefficient will not. I mean, when we prove the theory, we don't need that coefficient. So no problem.
So then without those or generated, you just consider a standard Kuramoto. You don't need to consider inertia. Right.
I mean, our first paper on archive is consider MJ is 0. And the second one is we consider sometimes MJ is 0, sometimes MJ is not 0. So it's a mix. It's a hybrid Kuramoto model. And for the simplicity,
I have a feeling that the inertia is very good. It's good. It gives you some decay rate. Right? Is this correct?
So, okay, I don't know how to answer this question, but for me, like, I think the damping, the D is the important factor for inertia. I mean, for second order Kuramoto model.
Yes.
And I only have intuition. I don't know how to prove it. So based on the conclusion that I will give, so all of the synchronization concept in real Kuramoto sense are equivalent, right? This means that if synchronization happen in the co-rotating frame, this means the dynamics of the dynamical system will tend to the equilibrium point. So nothing fancy happened. Nothing fancy, just equilibrium point. Okay, so equilibrium point is synchronization in real Kuramoto model. So what's the more interesting phenomena? For example, like periodic solution, right? So for the real Kuramoto, can we have periodic solution? The periodic solution means the real periodic. Okay, even in a co-rotating frame, can we have periodic solution? I think if we consider second order, but without the damping, D is 0. Sorry. If we consider second order, but this time D is 0, then we have a pure Hamilton system. And I think followed by Crandall-Rambino with argument, maybe we can bifurcate pure periodic solution if we don't have D.
Yeah, I don't understand. Do you claim that first order Kuramoto, the standard one do not have any periodic solution. Is this what you claim?
Yes, yes.
No. But people already know if there are 4 oscillators, omega j can be very different. All-to-all coupling, there is a chaos.
Yes, I know. But my point is, we need to in the co-rotating frame. The concept for chaos and the synchronization are different because my point is, I want to show all of the synchronization are equivalent to each other. So if first state happen, then this implies second and third and OPSs. This is my statement. So it could be some chaos, I don't know. But if chaos happen, it doesn't destroy this statement. So chaos, so chaos means the dynamical system will depend on initial condition.
And there's a
sensitive
orbit of periodic orbit, and there's a topological mixing. Yeah, there are 3 properties. This is a definite chaos. Yeah.
Yes, but you need to in the co-rotating frame.
Okay, we can discuss this later. Interesting. Yeah.
Yes.
Thank you.
So my point is, if you choose the co-rotating frame, then all of the concepts are the same. Okay. So this is the generic coefficient. So we consider omega lambda in parameter space. Okay, and generic means the omega and lambda are the dense and open. Okay, dense and open. This means that the bed parameter is major is 0. Okay, in this parameter space. Okay, so at the end we will show just major 0 things inside this space doesn't satisfy the generic conditions. Okay, because we want to use the differential manifold theory, SARS theory. So the statement is like this. Okay, so let's do our main theory. So the first theory is for generic second order Kuramoto model, and of course also the first order. For generic coefficient, these 3 concepts are equivalent to each other. Okay, this means tends to equilibrium point. This means the phase are bounded. This means the velocity theta dot tends to 0. Okay, so these 3 are equivalent to each other, and the bad coefficient is just major 0. Okay.
Do you know for which bad coefficients? What are the bad coefficients?
That's a good question. So even if this theory is very general, we claim for generic coefficients. But if you give me an yes.
I have a feeling there are so many equilibrium, and there are many settle points, settle equilibrium. Yeah, they are center.
You mean for the bad? You mean for the bad coefficient?
Those parameters are the bad parameters are those that give you such settle and settle equilibrium, and such that has a non-empty basis of attraction. This is what I claim. Okay.
Do you know how to construct the example for the bad coefficient? Because I'm also very curious about.
I don't know. But this is just my intuition. It should be something like they are settled, right? This settled the infinite manifold. They are major 0 because they are low dimension. They are not a whole space. And then when you have some perturbation, and this somehow this this basis of attraction becomes a four-dimensional, something like this. Yeah, but I think it's very interesting to describe those Bay parameters, I would say. Yeah.
Yes, that would be very good. I mean, for me, I also curious about, because we also try to use the numerical to find these bad things. But
how can you find
yeah, because the you know it's major zero and stuff.
yeah,
So
not
we
very
don't know how to.
Okay,
Yeah,
okay.
maybe I don't know. Yeah, but that's my, I don't know how to say, but at least we try. But okay.
Okay.
The next one is, if we focus on the O2O topology, then these four are equivalent to each other. And O2O means lambda is a constant here. Lambda is a constant here, not zero. Okay, lambda is a constant. Okay. Okay. And lambda can be negative or positive. Okay. So this is the O2O case. Now, we want to show something. So the first thing is full phase lock state imply phase lock state. This is by definition, because this means we have a solution tends to equilibrium point, and just choose a larger L, and this will happen, right? So as I mentioned before, this is just by definition. And from here to here, we have a very clever argument. It's like an energy argument. And for the second Kuramoto case, I recommend everyone to see Xia and his collaborator in 2019 in JDE. And of course, in our paper, we also prove it, because right now we have general M and general D, but that doesn't matter. So we just follow their concept. Okay. And so this is this implication. And the tricky thing is, how do we prove the reverse implication? Okay, so from FSS to PLS and then to FPLS. So that's our goal here. So the first one is, we want to show we have finite roots for generic coefficients. Okay, so I just typed down the SARS theory, and actually this is one of the corollary from SARS theory. And let me explain a little bit. So M is a manifold, and in our case, it's just R m minus 1. And X is a submanifold, and in our case, we just choose 0. Okay? And P is our parameter space. So in our case, is this one. Okay? M times m minus 1 and over 2. Okay? So P represents a parameter space. And we have a function f from let me write down the theta here, but later we will use psi. From theta and the parameter space, okay, to, I mean, the sum over sign, so it's also R n minus 2, or n minus 1. Okay, so if we substitute everything, this one is just 0, right? Because S is 0. And tangent space for capital M is just R n minus 1. So the same, right? Tangent space and this one are the same. And so the goal is, we want to show this is also R n minus 1. If that is true, this means F is transverse to X. And also this will imply, given for almost every parameter, this one is transverse to 0, and we are done. So by SAR theory, we just need to show this is onto. Okay, this is onto. So this is the goal, and let me do the calculation. What should I do? this one. Okay, let me do the calculation immediately. Okay, so let n is Rn minus 1, P is a parameter space, and M is the other n minus 1, and submanifold X is 0. Okay, so we minus, so we choose a fixed coordinate, let's say theta n. Okay, so what's our goal? We say theta psi 1 is equals to theta 1 minus theta n. Similarly, psi 2 is equals to theta 2 minus theta n. So psi j is equal to this one minus this one. Okay, and And finally, psi n is just 0. Okay, so we choose a new variable and we fix the degree of freedom for the less. So if we minus our original second order Kuramoto model, then we see this is for the j, right? For j, and this is for n. So we just add the minus the negative n term to each j from j is equal to 1 to n minus 1. Okay, so this is the equation 2. So this is our f. So our goal is to show this f is onto. Okay. Okay. So this is a motivation of the f. And now we have a lot of things. The first thing is, and also very simple. The first thing is we have psi, and we have omega, and we have gamma. So we want to consider df. Okay, and remind everyone, omega n can be represented by negative omega 1 to negative omega n minus 1. Okay, so we want to consider df for the equation 2. And a brutal calculation is, if we take the derivative with respect to omega, then for here we have identity matrix. For here we have a matrix with all 1. So we have 4. And of course, the rank is n minus 1, right? Because here. And if we consider the rank of df, so this one is n minus 1. So it's full rank based on the 4. So df is on 2. And to be more clear, df is on 2 means the first thing here, just r n minus 1. And on the right-hand side, the tangent space of n is just itself, so r n minus 1. So we are done. So we check the condition.
Yeah.
Yes,
I think
please.
essentially your computation just reveals that the parameter is linear in the equation. Can you go back to the Kuramoto model? Yeah, your f. Yeah,
yes.
You see? Yes. Your f. So no, your f, just your f. So fj.
Yes, here.
Fj. Your fj depends linear on omega, depends linear on lambda. So then that's not so surprising. If everything is linear, then of course when they intersect, they should intersect transversely.
Yes.
Thank you. Okay.
That's true. Yes. But this is just simple observation, but I mean, I'm also surprised. Yes. So
the main point is always Kuramoto is super nonlinear, but we want to find some linear structure.
Yes. But I think we also don't notice this 2 years ago, but recently we finally figure out, okay, we can, the comment that you make. Yes. So this means, what's the conclusion? The conclusion is, given parameter omega lambda, then for almost every lane, the FP is onto. So this means the DF, let me write down. This means D psi F, only psi. This is invertible, right? So our roots is isolated, okay, and this is true for almost every P, okay. So we are done. Okay, so now the bad parameter is just measure 0. Okay, so now we have the finite roots property for generic Kuramoto model. Next, to prove the first theory, okay, what's first theory? First theory is here. We want to show these three are equivalent to each other. Right now we have finite roots property. So we just want to cut our Rn-1 space, Euclidean space Rn-1, into a lot of 2 pi box, and then use the finite roots property to show the reverse implication from FSS to PLS. Okay, let me explain more. So first, because we consider the second order Kuramoto model, so first concept is we need to use this inequality. What does this mean? This means the first derivative can be controlled by the no derivative and the double derivative things. In our case, in our Kuramoto case, we consider double derivative here is smaller than constant times first derivative, right? Follow the theory directly. And the third derivative, right? So if we have this theory, then we immediately know we have this kind of thing. If FSS happen, this means the first derivative tends to 0, right? This means this one tends to 0. And because the triple derivative is bounded, so this implies second derivative will also go to 0. Okay, by this assumption, right? Okay, so let me explain more. So because we have second order Kuramoto model, so the first derivative based on the equation just just integration by just the integral factor. Okay, the first derivative is bounded by this one. Okay, for all t, and this is just initial condition. I mean, this one is bounded by 1, and this one is also bounded by 1. Yes, by 1, and this is just constant. So the first derivative is bounded. Okay, so let's go back to this one. So now what do we have? We have this one is bounded by a priori estimate. And of course, this is bounded, right? So this means the second derivative is bounded. Now, if we take the derivative again, then this term will give us first derivative and no derivative things. And second derivative is bounded. So this means the triple derivative is also bounded. So now, based on the form of the Kuramoto model, we already know if the first derivative is bounded, then the second and the third is also bounded. And based on the Landau-Kolmogorov inequality, we know if we are in the FSS frequency synchronization state, this means the double derivative will also tend to 0. Okay, so this is the first thing that we need to know. Now we are ready to prove the reverse version. So let me draw the picture because the concept is very simple. So again, we consider the equation for psi. So or maybe theta, but anyway. So we have this kind of thing, right? j minus plus dj theta j and minus mn theta n, right? Double derivative minus dn theta dot and equal to fj, right? Right hand side. And when right hand side is 0, this means equilibrium point. And we know we only have finite many of them. So we cut our space into a lot of 2 pi box. Okay. If FSS happen, if this one happens, what does this mean? By previous arguments, this means first derivative tends to 0. Also, the second derivative tends to 0, right? By a priori estimate and Landau-Kuramoto inequality. So on the left-hand side, this is 0, tends to 0. So, and we also only have finite roots. So let me draw something, finite roots for fj, okay? If phase log state, if this one is not true, what does this mean? This means our solution is unbounded, right? It's not true. This means we have a orbit tends to infinity, right? But because we only have finite roots and in a compact region here, so this means that we cannot pass if the trajectory is unbounded. This means we tend to infinity. But on the left-hand side, this one tends to 0. This means that at some point, the trajectory should go inside one of the box, one of the circle, because the center means fj is 0. So this will give us the contradiction. Okay, so the argument is not that terrible. So it's just we cut the space into a lot of 2 pi box. And because fj has finite roots, so in each box we have a lot of circles centered at the equilibrium point. If this one is not true, this means we have a trajectory go to infinity. But this cannot happen because at some time, the trajectory should go inside one of the circle. So this will give us the contradiction.
So
Okay.
your proof really relies on the finiteness of the equilibrium. And
Yes.
to prove this, you use a SAS theorem.
Yes, that's true. So actually, as you can see, our proof doesn't depend on, the assumption of our proof is very, it's not very restrict, because if we have the other kind of system, like more general things like a Kuramoto model, but without sign interaction, it's just like a general function, for example, like a gamma. Then if gamma have this kind of property, then our argument will also work. So because we just use the finite roots property and use this, argument is like a compact box argument. So we don't use the things in too many things in the Kuramoto model. And this is the details of the proof that I just draw the picture. So unbounded, and if you have a trajectory, then you have a lot of box. Okay, you have a lot of circle ball, then you got a contradiction. Okay, so next, you inside one of the ball, and you can shrink the ball even smaller, right? So at the end, you will go inside the equilibrium point. So this is just similar argument, but this is from phase lock state to full phase lock state. Yes. Okay. So because the picture is more clear than the words, so I just draw the picture for you, and I think this is more easier for us to understand. And so next, so now we finish for generic coefficients because we have finite roots property. So all of the synchronization concept proposed by mathematicians are equivalent to each other. So full phase lock state, and frequency synchronization state, all of them are equivalent to each other. Now, let's focus on a very special topology, all-to-all topology. Okay. So our first theory, although we proved the generic coefficient, but if you give us a specific topology, then we still don't know if the equilibrium state are equivalent to each other or not, because maybe that parameter is in a bad parameter set, but we don't know. So we still need to prove case by case. So that's the thing, which is not not straightforward. But let's consider the all-to-all topology first, because this one is the most classical one. So again, we have, I mean, I use different notation is because I copy paste from different papers. But anyway, so we have G here, and because lambda is a constant right now, and we want to show we have finite equilibrium point. Okay, so, okay, I didn't write down. Okay, sorry. So let me write down here. So we have G here, and the first thing that we want to use is this. Because we have these things, right? This thing is very good for us. So sum over per psi and over n. This one is a complex number, and let's denote this complex number by using this one. Okay, so what's our equation? Our equation is psi. So we times this on both sides. Okay. And this is, I mean, this right from now on, every calculation is from Kuramoto and Strogas, I believe. So we have this kind of thing, right? And what's the we have real part and imaginary part, and the imaginary part is just psi plus psi, right? This one. Okay, so right. So this means this can be rewritten by lambda r psi plus psi minus plus psi j. Okay, so this is just this one. So now the story is clear. If this one is 0, then we can solve this one, right? Because we only have one sign. So this one is just this one, maybe negative sign, is equals to this. So we can solve sine per psi j. Of course, we can solve cosine. So 1 minus this square, take the square root of this one, and maybe there is a sign in front of it. So let's use sigma j. Sigma j is just plus or minus 1. Okay, so right now we can express cosine, we can express sine. And again, followed by the order parameter, we have for the real part, we have this one, sum over cosine minus cosine j, right? And replace cosine. So this is just sum over j and the sigma j square root of 1 minus this one. Okay. So what's inside? So this one is omega j over lambda r. Now r is unknown, but the right hand side we only also have r, right? So this is one variable equation, and we know we only have finite choice. So we only have finite choice for r. Substitute r inside, we can solve psi j psi, and we also know if we shift this one, we also for each j, we also have the solution, right? S is just a random real number but fixed. Because of the translation invariant, we also have the other solution. So now in the translation invariant sense, we only have finite roots for O2O topology, Kuramoto. Okay, so this is a proof. And so that is why I write down the statement here. Okay, now what do we have? What do we have? So because in our previous argument, we consider capital Fj, right? Capital Fj means we fix the coordinate to be theta n, okay, and choose psi n to be 0, right? But right now we don't want to do that. For the O2O case, we just prove based on the translation invariant, we only have finite roots. What does this mean in the picture? This means if we still draw this, for example, this is the roots, but actually the roots looks like a straight line, right? Something like this. Infinite, I mean, so our roots is not, of course, not finite because we have translation. So can we fix one of the point? The answer is we still have initial condition, right? So theta j mj plus dj theta j is equals to omega j plus something psi, right? And again, if we sum over j from 1 to n, on the left-hand side, we have, I mean, sum over this one, nothing changing. But on the right-hand side, because we are in the co-rotating frame, so this is 0, right? This means n theta j dot plus dj theta j is a constant, right? Sum over this. This is a constant. Okay, so we do have the initial condition for this one. So this means we cannot have all of the line for our this initial condition case. We will collapse into a point. So we still have the finite roots argument. And this will help us to follow previous proof to show for the O2O case, we also have the equilibrium statement for full phase lock state, and frequency synchronization state. Okay, so the argument are the same, but the process are slightly different, but still the same. So right now, because for the O2O case, we also have finite roots property, okay, for all lambda, which is not 0. Then we have this statement, right? Now we can, because we already show for generic case, these three are equivalent, so we denote this concept to be SS. Now, for the O2O case, we already know SS will imply OPSs. This is straightforward because for the SS, this means we tend to equilibrium point. And so here, so we tend to equilibrium point. This means these two are, we already have the limit for R and capital theta. If the threshold condition doesn't hold, this means we have this property. And this will give us the contradiction immediately. So from SS to OPSs, this is quite okay. Okay. The tricky part is the opposite direction. So right now we want to prove the reverse implication. Okay. Now, sorry, Jiayuan, how many times do we still have?
Half an hour.
Oh, okay.
If you want,
so
no, I mean, it's already 1 hour, but if you want, I mean, maybe 10 minutes, maybe we have so many discussion.
Okay, so 10 minutes, okay. Okay, let me try. So based on, so for the O2 case, we have this expression for Kuramoto model. Okay, we can use capital R and capital theta to replace the sum over sign. So this is the key point. So this is non-autonomous system because the coefficient depend on T also. And if OPSS happen, this means there is R star and theta star such that these two will tend to R star and theta star. So we immediately get autonomous system here. R star and theta star are constant. Okay, now in equation 10, we are very happy because for each J, it's just a second order ODE with constant coefficient, right? So if we can get rid of, by using Poincare-Bendixson, if we get rid of the third case, the statement is complex. The periodic orbit and a connected set composed of the finite number of fixed points together with homoclinic and heteroclinic orbits. If we can get rid of these two cases, then we are happy. So that's the goal. Okay, this means that if we can show in equation 10, the only behavior is the orbit will tend to equilibrium point, then we are done. And why? Because, okay, now we can write down our system by using the, first order dynamical system. 2D dynamical system here, 11 to 12, okay? And of course, this one, sorry, only top. This one will tend to this one, right? Because this is our assumption. Okay. Now let's use the things asymptotic autonomous theory. So we have non-autonomous system, and capital F tends to small y. Okay. So this is the limit system. And limit system is autonomous system. So what's our goal? We use phi for y. Okay. So if the omega phi limit set of this limit system contains only equilibrium point, then follow this theory, we know the verified omega limit set for non-autonomous system, the original system, will have two scenarios. The first one is tends to equilibrium point. The second one is tends to the curve closed by the circle by the whole finite many phi equilibrium point, which are so let me use this. So something like this. Anyway, something like this. Okay. So our goal first is to show this statement. Okay. And after showing this statement, if this case happen, then we are done, right? Because this means the synchronization state happen because we tend to an equilibrium point. If this happen, this means our orbit will be a bounded orbit. But if our orbit is bounded, then we are also done because bounded means synchronization. So each scenario will give us the goal that we want. So now we want to get rid of the periodic orbit and the third scenario, a connection set composed of the finite number of fixed points together with homoclinic and heteroclinic orbit. Okay, so let's give a schedule proof here. So let's define the diagonal type function, which is this one. And this is nature because we have the kinetic and the dispersion term. Okay, and if we take the derivative of L, then it's not hard to see that it's this one. So the argument is just based on dissipation. Okay, and we just want to rigorize the intuition because we have a dissipation. What will happen? Everything should decay to equilibrium point. That's the intuition. So from 13 to 14, we have this property. Okay, now let's do this. So consider, because we know we have two equilibrium point or maybe one based on the inequality or equality. So we have equilibrium point called theta 0 for the limit system. Remember, limit system is just a 2D dynamical system with constant coefficient. Okay, so right now we have, for the limit system, we have equilibrium point. And here, I forgot to mention this one, sorry, go back. So in this case, our domain is R and T, not R and R. This is because we want to use the Poincare-Bendixson. And we know for V, it's just theta dot, right? And theta dot is bounded by previous a priori estimate. And for the theta j, if we set theta j in the torus, then this is immediately precompact. Okay, so every orbit is precompact, and we can follow Thing's theorem. We can use a Poincare-Bendixson. That is why. So on the cylinder, we want to get rid of the periodic orbit. So for example, if we have an equilibrium point here, actually we have two or maybe one. So let's do this. So if we have an equilibrium point here, if we also have a periodic orbit like this, and this orbit is non-contractible, okay? If we have this kind of thing, we want to say we will have a contradiction. Okay, so the winding number may be 1, maybe 2, but finite. Okay, so let's assume the winding number is 1. Okay, so we consider this set, and we consider this time. This times means originally the initial condition is theta 0 and V0. And how means using this speed, the first time that we hit the point, this one. Okay. If this happened, then if this is a periodic orbit, then the first time that hit this point, we will have the same speed. This means if we consider a Poincare map means we send the initial velocity to the velocity when t is tau. Okay. Because the initial velocity is V0. If we have a periodic orbit, then this must happen, right? P V0 is V0 because we just go back to the original point. Okay, so we have the same, not the same theta with theta plus 2 pi, but the same velocity, right? Okay, so this is the concept. So we can create a Poincare map, and we consider the how means at the initial v0, the first time that go back to the point, which is theta 0 plus 2 pi. And this is true because if we assume our solution is not bounded, okay, and we want to get a contradiction. So let's do the calculation. So because we have the Poincare map, and by this equation, if we integral this on both sides, then we have an integral with Vj squared, right? And substitute the definition of the L here. So we have the L minus final point minus L initial point. And this will give us 15. Okay, I just write down the solution here. And then we take the derivative with respect to the initial condition, V0, the parameter. Then we have 16. And later, based on the equation itself, we just times the integral factor, we have this one. Okay, and compare these two and evaluate t at the first time that go back to the theta 0 plus 2 pi, we have 17. And compare the 15 and 17, 16 and 17. If we take the derivative of 17, we have 18. Okay, and we have the tau derivative here, but this is just follow from the implicit function theory. So from 16 and 18, we can have this, but we got a contradiction because PV0 is equal to this number, and this number cannot be V0. So we just get rid of the periodic orbit for the limit system. Okay, now this means we can apply the thin theory. Okay, if we apply the thin theory, we have two conclusions, this or this. But as I mentioned before, either this or this, we are done. So from OPSS to synchronization state, it needs some techniques, but that's the process that I prove. I think I don't have time, but later, okay, very quick, like 2 minutes. So in our next paper, we show the complexified Kuramoto because motivated by previous result. In the real Kuramoto, in generical sense, we don't have any, synchronization is just converged to equilibrium point. Okay, so we don't have proper periodic orbits. Okay, and we noticed that in 2023, there is a group by physicists in Germany. They show in PIL, they propose a complexified Kuramoto model. And we found that this is very interesting. And so we follow their work and analyze the result. So in their paper, they say, oh, there is a periodic orbit. And this periodic orbit is pure. Pure means not even in the co-rotating frame, the period is still non-trivial. Okay, and in our paper in nonlinearity, we also find the heteroclinear structure and final time blow-up structure. Also, we calculate explicitly how large is period, how large the period is. Okay, so let me explain some of the results that we have. So this is the Kuramoto model, but only first order. And in our previous setting, we consider second order, but this one is more difficult. So we only consider the first order case. And Z is a complex number. Z is X plus IY. And this is okay because sine complex number is just sine coach sinh, right? So if we separate the real part and the imaginary part, we have a system equation looks like this. Okay, because we expand sine, and we have this one. Okay, and now we want to analyze what kind of interesting property do we have. The first one is if lambda is larger than the critical. What's the critical? In our previous slides, we defined this one is the maxima of the natural frequency. Okay. So if lambda is larger than critical number, then what will happen? We still have theory similar to real Kuramoto model, but again, no one proved it, so we prove it. So if the initial condition is inside a half circle, then this means this one, only real part. Then the complex Kuramoto can arrive at a frequency synchronization. Okay, and this is just because real part is bounded by a half circle, and then at the end, the angle will be below 90 degrees. So this 90 degrees. So this one is positive. And for the imaginary part, we can use the ground wall inequality. We can use ground wall inequality to estimate y. So y will tend to 0, and y dot will tend to 0 also. Both of them will tend to 0 exponentially. And substitute that result inside here and use the energy argument again, but this time is for complex version. So we dot xn on both sides. And then because y minus y will tend to 0, y dot minus y dot will tend to 0 exponentially, then we can estimate energy, and we know Sn dot will tend to 0 also. So this is the idea of the proof. Okay, and the second thing is, because in a complex Kuramoto model, the finite time blow up may happen. So there is some issue like a well-defined, well-posedness issue. So I mean, global existence issue. So for the real Kuramoto model, we don't need to worry about this because omega and psi are bounded. And based on the exponential criteria, we know in real case, the solution will exist globally in time. But for the complex version, the situation will be tricky. So if the initial condition is pi minus delta, delta is a second in the second quadrant. And so this is in the first quadrant. So sorry for the notation, but we try to consistent to our previous paper, so we use this notation. So if the initial condition is in the first quadrant, then global existence is fine. So this is the theory. Okay, so we solved the issue for the global existence, but what's the new dynamical system behavior? So we focus on the two oscillator first. So if we only consider two oscillator, we have this one, okay? And a straightforward calculation is C, this quantity, is a conservative quantity along the trajectory 20. So if we take the derivative of C, then we have this one, these two relation can use. Okay, then we have the 0, dc dt is 0. Okay, so if we have conservative quantity, then everything is fine. If C has a closed curve, then we may have the periodic orbit, right? So this is a condition. If the initial condition is here, then we have periodic orbit, and the period is this. And so the periodic orbit is just because if the initial condition C is a conservative quantity, is larger than this number, for weak case means lambda is smaller than omega. Okay, so if this is the case, then C is close. The curve is close. Okay. Sorry, I should draw the picture. So this is the equilibrium point. This point is 2 pi, comma, in the R2 plane. Cosine, coach. Oh, I cannot write down. Okay, 2 pi over 2, coach, omega over lambda, inverse. And this is well defined is because omega is larger than lambda, right? And of course, the minimum for core G is just 1, right? So, and we only choose the positive branches. So this one is well defined. And what's the periodic orbit? C looks like this. If C is larger than this number, okay, it looks like this. And this is the closed curve. And we want to show the period. How? Because we are in a complex system, so we can use the residue theory. Okay, so this is the calculation. So we have Z dot is equal to F, right? And F is omega minus lambda psi. And we separate it, dz F P. In one period, this is if the Whiting number is 1, then this is just period T. And we just need to use the residue theory to calculate this. And the brutal calculation, not brutal, is easy calculation is this one. So we got a periodic orbit. And of course, the gamma, I mean, this one, the gamma is a curve center at this point. Okay, and this is an equilibrium point. So we got a period by using the residue theory. And the final thing is we have finite time blow-up condition, and this is the initial condition. On this initial condition, we have this one, and we can rewrite our system only by using the X, okay? And in each case, we know this will finite time blow-up, and that's done. So thank you so much for your attention. I'm sorry for the late. Okay, thank you.
Thank you, Ting-Yang. Thank you very much for giving us essentially 2 talks. Okay. Yeah, and for the first part about the equivalence of all these synchronization notions, that's very useful for us, right? Because we don't need to publish so many papers. And for the second part, the complex file Kuramoto model exhibit many intricate dynamical behavior. That's also interesting. Okay, so any question, comment, remark from the audience, just unmute your microphone and just ask, please. Maybe let me answer the first question. I want to understand your result. It seems to me that the FPLS, something like a phase synchronization, is the strongest one. Of course, in the end, they are all equivalent. Okay. So if I am a mathematician, I should always use this notion to do my analysis, right? But for scientists, I think the real value order parameter synchronization is the most difficult one. Yeah. But still, I am curious, if you want to prove the equivalence to the real order parameter, what happened in your group, in your argument? What's the gap? So I cannot see this very quickly. Can you still use Bendix and similar argument? Because when I converge, they should somehow give some constraint on the convergence of Z, right? They are not really independent to each other. They are kind of related. Yes. So can you comment on this?
Yes, this is a good question. And so just based on the progress that we have right now, because we rely, sorry, can you see my slides?
Yes.
Because right now, we rely on this. R tends to this one, and this one tends to this one.
And suppose only R converge.
Yes, only R. Then 12 is still a non-autonomous system, right? I'm not sure.
I see.
I think, yeah, I think there. I think there will be a gap in our argument.
Do you need that theta converge, or is it also fine if a theta has a bound?
Yes,
I
that's true.
I don't know. But now I see.
Yes.
You want to
But
really have.
I believe your intuition, because based on the numerical, I mean, they always happen at the same time. So so I think this will be a good question. Yes.
Okay.
And I also don't know how to show it right now. Yes. I have no idea. Yes.
And this is also interesting because somehow if you assume OPSS, then the dynamic is essentially two-dimensional. It's essentially two-dimensional, right? And
Yes.
that's why you can apply the Poincare bandit. And this reminds me of the Watanabe-Strauss transformation again. Of course, they consider the equal natural frequency, and now your natural frequency omega are different, and so there's no Watanabe-Strauss. But if you assume you are in the invariant subset of the OPSS, then it's essentially two-dimensional. I am curious whether you can connect your discovery to this Watanabe-Strauss. Yeah, no, but this is just a common, okay?
And by the way, for their Watanabe and Strauss transformation, Watanabe Strauss transformation, can we also apply their result to second order Kuramoto model?
There's no such Watanabe. I don't know. I don't know whether there's such transformation for the second order setting. I don't know.
Yeah, I think they focus on the first order, right?
Yes. Equal natural frequency, first order. Yeah.
Yes.
I mean, because somehow you just show us a very good reduction of dimensionality, right? And this is this is very nice. Very nice. Yeah. Yeah. Okay. Good. Further question, comment, remark? There's still 2 minutes. Maybe let me give. Yeah, please.
Sorry.
Hao-Ze.
Hi.
Please.
So firstly, if my voice is clear,
Yeah.
could you please return to the definition for the synchronized state?
Okay. Can you see my slides right now?
Yeah, of course.
This one?
Yeah. So generally, you don't use the torus setting, right? So you suppose the domain is R. So
yes.
So don't you say
for the first three we use R, but for the final one, because we want to use the Poincare band distance, and one of the conditions is precompact. So if we choose R, then we don't know if theta is bounded or not. That's the issue for us, right?
Okay.
So we choose the torus for theta at that moment. So the precompact condition is automatically okay. Sorry, what's your question?
I see. So for the OPSS, I mean, you using the order parameter, so you have the torus assumption.
Yes.
Oh, okay. I see. So
sorry, not the assumption is we choose torus first and use the Poincare band distance to get one of the three outcomes. I mean, statement from Poincare band distance. And if we have a periodic orbits, this means on the R, we have a solution which is called drift solution from 0 to 2 pi and then to 4 pi and go on.
Yes.
And at 0, because this is a periodic orbit on the torus on the cylinder, so when theta is 0, then the velocity is called v0. When theta is 2 pi, because the periodicity, so the v is also v0. When theta is 4 pi, the v is also v0. So that's the scenario when we lift the orbiter from cylinder to R2. Is that okay for you?
Okay, I see. So since it's quite strange to use the order parameter if you have a long compact space, since it's no longer being the center of a mass.
Do you want to make sure what happened for this assumption to this one, or what do you mean?
So you only consider all the parameter in the torus setting or something compact space, right?
No. We consider OPS as in Rn.
Oh, okay.
But
so the
yes,
physical meaning for
because of the restriction for the Poincare-Bendixson argument is we want a pre-compact. So we choose cylinder first and then lift the orbiter. So the lift orbiter is still in the R that you want. Yes. So
okay.
same. So I mean, we don't lose any information. It's just the same thing. But
Okay, see.
yeah, but we do need some information from Poincare-Bendixson, so that's why. Yes.
Okay, thank you. So because now time is already time's up, and so if you want to stay and discuss, you are very welcome. And for the audience who want to leave now, feel free to leave. And I will stay here to discuss with our speaker, Ting-Yang. Okay, you are very welcome to stay, but see you next time, okay, for our webinar talk. Thank you for coming. Thank you.
Thank you so much.
Bye.